And let's see here. Okay, so welcome everyone to lecture 10, which I will do on this iPad now, and hope that this works. Otherwise, I mean, I hope to be back at ICTP by the blackboard by next time. So you can tell me at the end what you preferred. So hopefully we will have as little technical issues as possible today. So first, I just wanted to start by making some kind of by adding something, some correction, if you want, from last time. So about the proof of the fundamental theorem of algebra. So we said that. So if you recall the proof, we said that we assume that P of Z is never zero. And this implied then that 1 over P of Z was an entire function. Okay, and then we wanted to conclude by saying that this, the absolute value of this entire function was bounded, and then by Liouville, this is supposed to say that 1 over P is constant, and hence P is constant, and this was a contradiction. So then so there was a question, why is this true? And I mean, the reason for this is simply, so morally speaking, the reason was, so we got some answers from our students, but they just wanted to address it again. So morally speaking, it's just that the polynomial goes to infinity at infinity if you want, and it's bounded everywhere else. So you can just write this as the absolute value. I mean, if you want to write it formally, you can just write it like this. Sorry, not equal, but times the absolute value of, so 1 plus an minus 1 over an times 1 over z, and so on. So the last term here would be a0 over an times 1 over z to the n, I guess. So something like that, and then you see that this thing here, it will tend to infinity as absolute value of z goes to infinity. So let's put it this way. And this thing here, well, this one will tend to 1 as absolute value of z goes to infinity. Okay. So, I mean, what I wrote here was, of course, so this is absolute value of P of z. Take it in the same color. Is equal to this. So, so then it is clear that this bound here must hold. Okay, so I hope you can see that along these lines you get this claim. So I hope this is enough details on that point. So is this clear now for everyone? Okay, very good. So then let's, after this little parenthesis, let's go to what we were doing. So if you recall last time, we just proved that holomorphic functions are analytic. So that holomorphic functions have a power series expansion, right? And I think we finished this proof at the end. And then we said that yeah, I drew this picture with the analytic continuation, okay, that we started discussing. And this one was leading up to something called the Identity Theorem, which is about zeros of holomorphic functions. So the next headline here would be zeros of holomorphic functions. So if you want, so zeros of holomorphic functions, they sort of symmetrically correspond to poles. So, which are then singularities, of course. And in the sense that, I mean, the example would be that if I write down some some rational function. This would be a very typical simple example. So it's rational. Then, of course, if you have 0 of f, then it gives a 0 of h. So assume no common zeros, okay, so as usual. So fg, just to be on the safe side. Okay, and then if you have 0 of g, then this implies, using this no common zeros assumption, that h of z has a singularity at this point where the denominator vanishes. So, I mean, rational functions are a very typical example. In fact, Neuromorphic functions on the extended complex plane on the Riemann sphere will be exactly the rational functions. So this is an important example to understand. Okay, but so why am I saying this? So I'm saying this because what we will be showing now is that if you have a 0, or the set of zeros of holomorphic functions is discrete, so zeros are isolated. And since they correspond to poles in this way, so 0 of f is a pole of 1 over f, and so on. So this will mean then that, in particular, both zeros and poles will be isolated of holomorphic functions. So of course this is something quite special. I mean, a strong result. In general, a singular set could be anything. But now the claim is that if you have holomorphic functions, then the set of singular points is just some discrete set like this. Could be infinite. Okay. For example, we could have zeros or poles in every integer or something like that. Would be kind of a typical behavior. So the theorem, the formal statement for this would be the Identity Theorem. This is the Identity Theorem. And it says the following, so let f be analytic, be holomorphic. Again, these are used synonymously. On an open, connected domain, U. Then the following, I will give 3 claims that are all equivalent. So we have the first one, which is that f is identically 0 on U. The second one is that there exists some point A in U, such that if you look at the nth derivatives, then these are 0 for all n natural numbers, okay, for all. And then you have a third one, which is that you have a sequence of points zk that tends to A, okay, so, but never equals to A, for some A, such that f of zk is equal to 0 for all k. So what this means is that there is some accumulation point, right? So you have A here, and then you have the zk, if you can see this, that will tend towards A. And these are all zeros of the function, so this means that there is a so-called accumulation point for the set of zeros. Okay, so we have this result. And a very common application. So how should we try to use this? So common application. And indeed, I think you all understand this application now, because this is what you were supposed to use in the homework. So it's that if you have two functions, so of course this thing with saying that f is equal to 0, you can apply it to, if f minus g, if you look at this, so you have two functions, f and g, and when you look at their difference, then you get the following thing, so that f of zk is equal to g of zk. So for all k, where zk has an accumulation point. So for example, it could be a sequence that tends to 0, like 1 over n or something like that. Then it means that f is equal to g everywhere. Okay, so what this means morally is that if you have that holomorphic functions, if you have two holomorphic functions that coincide on some set, even that only has an accumulation point, then they have to be the same function. So in particular, this is true for some open set or something like that. So if they are equal on an open set, then they are equal on all of you, so to speak. So it means that holomorphic functions are quite rigid, right? That if you cannot have two holomorphic functions that coincide in a sort of large set in this sense of this theorem without being actually the same functions. Okay, so now we will prove this theorem. So any questions about this statement before we do that? Okay. So the proof is actually very nice. I like it a lot. So, okay, the proof is goes like this. So we show that 3 implies 2, implies 1, implies 3. Okay. So for the first step, we do the 3 implies 2 part. So what do we have to show? So sorry, I will just go up to remind you. So we show that if there is a sequence like this, where f of zk is 0 for all of these zk, then we want to show that somehow, for some reason, these derivatives have to vanish. Okay, so to see this, we notice, so we have this zk that tends to A. And then by continuity of f, we have that f of zk, which are all 0, tend to f of A. Okay, so in this picture, and this implies then that f of A will have to be 0 as well. So this is the first thing. And then we assume, so we want to show that all of these derivatives here are 0. So we assume that they are 0 up to a certain point, because now we verified it here for the function value, right? So for j equals 0. And now we assume that this is true up to n minus 1. So then we can expand. So we expand f in a power series because it's holomorphic. So we expand around the point A. We get the following by the theorems that we have seen. The coefficient is given by precisely this. And this is equal to, so I can write this as z minus a times n to the power n. And let me call this part that is left, let me call it fn of z. So remember n was this thing here. So so you see what I do, of course. I mean, I assume that all of the first derivatives were 0, so this sum here starts at n. And so then I factor out this z minus a to the n from here, and I'm left with something. And the thing I'm left with is analytic. Okay. And its value, what is the value of this fn of a, so the remaining things? So this sum, it starts somewhere, and then I factor out this thing. So what would be the value? Anyone?
Excuse me, Professor, I don't understand what we are doing.
You don't understand what we are doing. Okay, so we are trying to show that, so we are looking at this identity theorem, this theorem here, and we are trying to prove a theorem. So to prove a theorem, we want to show that all of these 1, 2, 3 are equivalent. And to do that, we show that 3 implies 2, and 2 implies 1, and then 1 implies 3.
Okay.
Okay, so the point that we are now doing is that 3 implies 2. So we assume that there was this sequence of zk. I mean, zk tends to a. You understand this third statement here? You have this accumulation point.
Yeah.
And then, so we assume that, and we want to show that then all of the derivatives must vanish. So we used this hypothesis to show that so all of these are 0, but zk tends to a, so then f of a has to also be 0. Okay?
Okay.
And then we wanted to show that if f of a is 0, then also f prime of a must be 0, and so on. So we assume, so by sort of induction here, we assume that the jth derivative was 0, but j could be 0, so this could be assuming that f of a is 0, right?
Okay.
And then I get the power series expansion here. And so what is happening, I mean, of course, since these things here, they are equal to 0 for k less than or equal to n minus 1, right? So this thing is just equal to f of n of a over n factorial times z minus a to the n, and then plus a bunch of other terms, right?
Yes.
And so then when I factor out this z minus a to the n, and I write fn for what is left, and the leading term of fn will then be, will just be this fn of a. So when and when I plug in, I mean, then all of the terms here will be higher order terms, so this will be, fn plus 1 of a over n factorial z minus a to the n plus 1, and so on. So when I plug in z equals to a after having factored out the z minus a to the n, then of course this one will be 0 still. So everything else will be 0, and fn of a will just be equal to the nth derivative divided by n factorial. Is that okay?
Okay.
Okay, so we're not quite done with the proof yet. So we have this, and then we wanted to say that. So now we want to conclude. So how do we do that? So we try to recap what we had. So by definition, f of zk was 0, and we now showed that by the above formula, then f of zk was equal to z minus a, so zk, minus a to the n times fn of zk. And since zk, but for zk not a, this implies what? So what does it imply about fn of zk? So you see here that this product is equal to 0, but if this one is not 0, because zk is not equal to a, then it means that this one has to be 0. Okay, as you will know from the algebra course that you're having. or many earlier algebra courses that you took. So this one is equal to 0. On the other hand, this one will tend to Fn of A by continuity. So Fn was analytic, so in particular, it's continuous. Okay, so it tends to Fn of A. And this implies that also the nth derivative of A has to be 0. So what we showed is that we used the hypothesis to say that, to recap a bit, we showed that f of A is 0. Then you go through this argument here to show that f prime of A is 0, if you wish. But then we wrote it down to say that we assume that the first n-1 derivatives are 0, then also the next one has to be 0. Okay? So using this, of course, it implies that all of the derivatives are 0 for all n. And so this proves that 3 implies 2. Okay? Because the second point was that all these derivatives vanish. Okay, so any questions about that? Was it clear in the end?
Yeah, it's clear.
Okay, thank you. So then, okay, so I said it was beautiful. So the first part maybe wasn't so beautiful. It was just standard. But this 2 implies 1. So this uses a beautiful, worth writing down, uses a beautiful idea. That's a very classical idea at the same time. So what we need to show, let me first remind you. So this scrolling works here. So what we need to show now is that we assume that all of these derivatives here are 0, and we want to show that then the function itself has to be identically 0. Okay? So how can we do that? So the very classical idea is that we consider, so I will write down this line, and then I will ask if someone has seen this kind of proof before. I guess you might have. So let me write A for the set of all the points Z where these derivatives vanish. But not only where they vanish, but where they vanish for all positive integers, right? Okay, I mean this. So you look at the set in Z where all of these vanish. And then we want to show that actually this set A is equal to U, right? Because what we wanted to show was that f is 0 everywhere. Okay? And now, how do we do this? So has anyone seen this kind of proof before, and anyone maybe knows what I am about to do? No? Okay, so it will use topology as a hint. Okay, so how can I show that A is equal to U? If you haven't seen this before, it's something that at least I see a lot, I mean, around in research talks and so on. It's kind of a miraculous method from topology. So the idea is to show that A is, first of all, non-empty. But second of all, we want to show that it's open, and we want to show that it's closed. All of this in U, right? And then if A is a non-empty, open, and closed set in U, then what does this imply?
Well, it's equal to U.
Exactly, because just the open and closed, it means that it's either empty or the full set by topology. But since we also show it's non-empty, then we would be done. And for some reason, this is a very powerful tool that you see everywhere in mathematics. It's a very nice trick, so you should definitely learn it. So in our case, let's verify that it's non-empty. So this is true because the point A is in here by assumption. Okay, because we were assuming that there was a point A where all the derivatives vanished, and we wanted to show that then the function must vanish everywhere. So this one is true by the hypothesis. Then to show that A is closed, then how can we do that? So we have this set, and why is it closed, would you say?
It's the intersection of closed set.
It is the intersection of closed sets, okay. So which intersection?
For each n, the Fn equals 0. Because Fn is continuous, so the inverse image of 0 is closed.
Okay, very good. So you're saying that A is equal to this intersection that I just wrote?
Yeah.
And you say that the nth derivative is continuous?
Yeah, so these are closed because 0 is closed.
Exactly, which implies that A is closed because this singleton set here is closed. Okay, very good, excellent. So we now know as well that it's closed. And now the last part, so the slightly harder part, but not too hard, is to see that A is open. So how could we try to see that it's open?
I think by continuity, if f is not 0 at a point, then it's not 0 in a neighbor.
So then, but if it's not 0 implies not 0, then you get the closedness, right? I think you're. So what you want to show is rather the opposite, right? That if you have a 0, then you have an open neighborhood where everything has to again be 0.
Yeah, sorry.
Yes. So the idea here is to use somehow the power series expansion. Because power series expansion is a tool, right, where you know something in a point and you want to know something in a small neighborhood locally around that point, then power series expansion is a very natural tool, right? And in particular, we know something about all the derivatives, and this is exactly what appears in the power series expansion. So we assume that Z0 is some point in this set A. So not necessarily this small a that we started with, but we take any Z0 here. So then we can expand as a power series in the following way. And divided by n factorial, z minus z0 to the n. And there is some radius of convergence. So which is positive, sorry, not larger than 1, but which is positive, of course. So there is some radius of convergence such that this holds. So yeah, so this holds on this disk centered at Z0 with radius r. Okay. But now we have to remember we assumed that Z0 was in A. So assuming that means that all of these partials here are 0, right? Okay, so all of these partials were 0, and this implies that that f of z is 0 in all of this neighborhood. But this is not enough. I wanted to show that actually the partials were also 0, because, I mean, remember the set was defined in such a way so that I asked that all of the derivatives were 0. So then I also have to, based on this formula, I can also differentiate it. So what is the kth derivative here? I also have to look at this one. So the kth derivative, I can write it. So if I don't use the sum notation for once, it's equal to this. It's equal to something like this, plus k factorial over k plus 1 factorial. Okay, so now I guess I'm copying some computation I did. But you know simply that you can differentiate term by term with f of z. We saw this earlier in the course when we were talking about power series expansions. And this will mean, so again, by assumption, this will be equal to 0, this will be equal to 0, and so on. So the conclusion will be that fk of z is equal to 0 for all k natural numbers, and this is true for all z in this small disk, small open disk of radius r around z0, and this implies that this disk is then contained inside A. So A is open. Because for any point z0 in A, we could find a small disk which was also inside. And then to repeat, I have what I wrote up here, that since A is non-empty, open, and closed in U, well, by topology, we have no other choice than saying that A is actually equal to U. Any questions about that? Okay, and finally, by the way, the 1 implies 3 is obvious, right? So if I go up, this thing here, that 1 implies 3 is obvious. Okay.
Professor?
Yes.
Where we use connectedness of the domain U, where in the proof, where we use this condition?
Yes, very good question. So we use this condition here. So this would mean that, so more precisely, this means that A is equal to a connected component of U. Right? So this is what topology says. So if you have a set, so if you have a set which is open and closed, then it means simply that it's equal to one of the connected components or it's empty, if you remember this result. So it means that, you know, if I didn't assume that U was connected, then I would not know for sure that A is all of U. So this is where I use it in the conclusion. Is that clear?
Yes, it's clear.
Okay, good. Okay, excellent. So to recap, so the corollary of this and the takeaway would be then that zeros of holomorphic functions are isolated. And this is of course true unless f is identically 0. Okay, so some examples, if you wish. We could take sine of pi z. So what would be the zeros of this function? Okay, so of course it's zeros in the multiples of pi. So it has all the zeros, all the integers are the zeros of this function. Okay, but on the other hand, so it is entire, if you want, so it is entire. And you can see how so it is holomorphic in the entire complex plane. It has infinitely many zeros, but they are isolated, so it does not contradict this theorem. On the other hand, you can look at sine of pi divided by z. So what would be the zeros of this?
1 over n.
Yeah, okay, so in 1 over n, where n runs over the...
And z.
Yeah, okay.
Sorry.
Okay, oh, sorry. Yeah. No, you're right, it's z. So zeros in 1 over n. So what does this mean?
It has essential singularity as at 0.
Yes, so 1 over n has an accumulation point. And very good, you already know about essential singularities. So accumulation point in 0. So in particular, it is not entire. And yes, it has an essential singularity in zeros. Okay, so now we know that zeros of holomorphic functions are always isolated. And I hinted earlier by the example of rational functions that there is some connection between zeros and poles. So that will show that also singularities, the ones that we are interested in, are often isolated. So a warning is that not all singularities and not all weird behavior of functions is because of an isolated singularity. So there are much worse things that can happen. For example, you can have the branch cuts, that could be seen as a singularity. If you remember the square root and the logarithm. But yeah, so these things can definitely happen. But what we will study now is what happens with isolated singularities. And this is already covering very much of the possible behaviors you can have from holomorphic functions or what we'll call neuromorphic functions. So then you have the following definition. So just to tell you what an isolated singularity is and what we mean by that. So an isolated singularity of some holomorphic function u to c on some open set as usual. So what we mean by that is a point in u such that if I remove this point and restrict the function, so this restricted function should be holomorphic. Okay, so I just have some u, and then I remove this bad point a, and it is holomorphic everywhere outside. So this means that even if it is possible to define my function in such a way that it becomes holomorphic, then it can still, technically speaking, be called a singularity. But this is somehow a little bit stupid. So this is what we call then a removable singularity. It means that our function might not be defined there right now, but we could define it there so that it becomes holomorphic. And the example of something like this would be you know, sine z over z, where it's not immediately obvious what happens actually when z equals 0, but it is a removable singularity. Okay, so three types of these singularities. So there's the removable singularity. There are the poles, and there are the essential singularities. So we have already seen what it means to be removable, right? So we have seen about the removable ones. We have seen that the definition is that the limit as z goes to a, so it's removable at a, if this thing here is equal to 0, and then f extends to a holomorphic function on all of u. If you remember that we did this, and the example was this. I mean, one example would be sine z over z. You can go back to that. And then you have the poles, which is what I will talk about next. And then you have the essential singularities, which is a word that Hagar, you used right now. And what does it mean to be an essential singularity? So the slogan would be somehow that it's a singularity which is not a removable singularity or a pole. So an isolated singularity, I should say, which is not removable, nor is it a pole. And an example of an essential singularity would be something like the e to the, like the exponential e to the 1 over z or something like that. So this one we'll look at later. But so the topic that I'll focus on in the next few slides here will be poles, and poles of order n, more specifically. So we'll talk about poles of order n. Okay, so first we recall, because we never really talked about, at least not very formally in this course, the order of a zero of a holomorphic function. So we recall that the order, the order of a zero of a function f at the point a in u is defined as the unique, let me just write this, as the unique capital N in n such that what? Such that f of z is equal to z minus a to the n times some other function h of z, with h of z holomorphic. So of course here I mean a holomorphic function, right? So to be clear. So this one should be holomorphic in a neighborhood of A, and it's not vanishing in A, okay? So this is an important point. So what does this mean? So now we're talking about the order of a zero, right? Just as a preparation for the poles, because it's going to be a very similar thing. So it means that its power series expansion, you can think about what it will look like. So it will be of the following form. See if anybody has the answer.
It's summation from n equal 1 to capital N, or a minus n, because we will use n again. Anyway, over z
Now it's
minus
a 0, right? So just to say it's a 0 and not a pole of order n.
So it starts from capital N.
Exactly. So the correct answer is that it starts from capital N, because I mean, so Haga, what you were saying, it sounded like you were trying to say for a pole.
Yeah.
Right. So for now, it starts at capital N, goes to infinity of this an z minus a to the n. So the only point is this, but the first non-zero term here, where an is non-zero. So this is exactly what it means with the order. So it means that this corresponds. So because what is the an? Well, it's the nth derivative, right? So it corresponds to the smallest n natural number such that this derivative, the nth derivative, vanishes. Doesn't vanish, sorry. Because it corresponds to the first non-zero coefficient here, right? And here I should write a n not 0. Okay? So this is the order of a 0. Now, what is the order of a pole? So first, I need to... So suppose that f, so we are in this situation when we're talking about poles, so we have this function where something special is going on in this point A, but it's holomorphic outside. But f of z goes to plus infinity, or plus infinity, goes to, what am I saying? So it goes to infinity. As z goes to a, so we have some singularity. So this could be either a pole or an essential singularity. By the way, this error of writing plus infinity here is kind of stupid, right? Because it's complex valued and we have no order. So don't do that. But it's easily done, just out of habit. Okay. So the definition of the order of a pole, so the key definition that you have to know is this, that the point A is a pole of order n. Okay. For f, if and only if A is a 0 of the same order, but for 1 over f. Okay? It's a pole of order n, if and only if for f, if and only if it's a 0 of order n for 1 over f. And again, we then get this this sort of duality between zeros and poles. This is the slogan that I employ. So the example would be that, if f of z is equal to some function with some power series expansion like this, which starts at n because it has a 0 of order n, and this is holomorphic. Okay, so 0 for the n. Then what about 1 over f? Well, then this one will have a pole. So I didn't want to write down what it was, but it has a pole of order n at A. And of course, both f and 1 over f are holomorphic on the set U minus the set of zeros of f, or poles of f, I guess. Okay, let me just remove this. It's not important anyway. Okay, so this was just a warm-up example. Now, let us continue in a similar way. So let us assume that 1 over f is analytic, holomorphic, at A. Then what can we say about the singular behavior of f? Well, what we say that it's, morally speaking, it's kind of nice. And what do we mean by nice? So by nice, we actually mean, it might not seem like it, but the not nice thing would be an essential singularity, and the nice thing would be a pole. Okay, so it would be a pole. So, okay, so what we have is the following. So let n be the supremum of this. So this will be a running example actually. In this example, it will lead to the definition of the Laurent series. So let me just write here toward the Laurent series expansion. Okay, just so you keep this in mind. So I will take some small parenthesis break here to define what the neuromorphic function is at some point, but otherwise this will lead to the Laurent series. So if you take capital N to be the supremum of all this k such that 1 over z minus a to a k times 1 over f of z has a removable singularity, at the point A, look at this, this thing here. This is an important definition. So then what can we say about things? So it has a removable singularity. So this thing that I just wrote down, so if I take n to be the supremum, then in particular this one is analytic, because of the removable singularity theorem that we have proved, right? If you remember, we proved that removable singularity means that the function is analytic. So this one is analytic, which means that it has a power series expansion, again, so we use the same thing over and over. So it means that, so this function that was over here, it's equal to some like this, where we haven't said anything about the order of any zeros or something like that, so it's equal to this. But then what does it mean? So 1 divided by z minus a to the capital N times 1 over f is equal to this. Okay, but this means that if I look at z minus a to the n, f of z, then, so this comes, here comes the sort of claim here, if you want. So can I write this as a power series, is the question now. So then this would be 1 over all of this sum of an z minus a to n. Okay, but can this be expanded in a normal power series if I divide by power series? Or not? So what do you think? Okay, so let's look into it. So let's leave this empty then, and let's make a little parenthesis here about division of power series. Okay, so first of all, if you have something like this, so this is a well-known thing, right? Then what is this equal? If you expand this in an infinite series, it starts with 1. Then come minus z plus z squared minus z cubed, and so on. So you recognize this, right? So then when I have, so if I have 2 power series, let us even write this even more generally. So I have 2 power series and I want to divide them. Then what do I do? So of course I want to put it in the form that is up here, right? So what I have to do is I have to add and subtract 1 from this somehow. So I write this as, so this one I keep it the way it is. And then I can even, okay, I can take out also this. So now it starts with 1. Okay, so I can write it like that. And so in other words, this is equal to B0 times the sum of this times, and then using this thing here, right? I get here that it's 1 minus, so let's call this thing here B. It's equal to 1 minus B plus B squared minus B cubed, and so on. Okay, but so then what you have is you have all this sum that starts at n equals 0, and you have the sum that starts at n equals 1 up here. And then you just multiply them all together, and I won't ask you to exactly to determine these coefficients, Cn, but the point is that this is also a sum that starts here. And
Shouldn't B be smaller than 1? Shouldn't the norm of B be smaller than 1 for the expansion?
Ah, yes. Yeah, you're right about that. Yeah, so okay, so let me give the formal statement of this this expansion. So let me give a binomial theorem. Let us recall this, since it's related to your question. So this is equal to, okay, so the point here actually, so of course everybody knows the binomial theorem for positive integers. So the point is you have a binomial theorem for any complex number, okay? So this is something that I wanted to mention anyway. So this is equal to this 1 plus, I don't know, a1z plus a2z squared plus and so on, where an is equal to this a choose n, I guess you say that in English, I'm not really sure. But anyway, it's the number that's defined in this way. divided by n factorial. So in this case, you'll be able to see that an over an plus 1, this goes to 1, as n goes to infinity. So if you check this, and this will mean that the radius of convergence here is equal to 1. Okay, so here the radius of convergence is equal to 1. Now, your question was about this series, but the absolute value of z should be less than 1. So to be completely honest, I don't remember these things super well. So you want to speed. But so regardless of what the radius of convergence is, then I guess Younes asked the question maybe. So regardless of the radius of convergence, I mean, so we factored out this 1 over b. So maybe by factoring out, I mean, so what you want here is, of course, that the absolute value of b here is not too large.
Yeah, maybe we work on a sufficiently small neighborhood.
Yeah, but actually, it's not about the radius of convergence of these series, sum of bn, right? But it's just about the value of this series. So I think you can just, yeah, I mean, in either way, I mean, however you want to put it, you're going to arrange so that this thing can apply. But I think you can do it maybe, looks like you could do it maybe just by the thing that you factor out here.
Yeah, if we take a smaller neighborhood, we can have b with a norm smaller than 1.
Yeah. Okay. So anyway, the point is that you get this kind of power series expansion in a suitable way. And so when I go, and you should remember this binomial theorem, by the way, this would be useful to know that it exists also for complex numbers. Okay, and so now I wanted to fill in what did I want to write here? Okay, and what I wanted to write was just that it's equal to the sum, let me take the same color. So it's equal to the sum of some Cn z minus a to the n for n greater than 0, okay? So just for some Cn, complex coefficients here, okay? But this means that f of z is of the form, you know, c minus n over z minus a to the n. It's of this form. So it means that, okay, here for those of you who know what the Laurent series expansion is, you will recognize this as, you know, you have a singular part here, apart from the usual power series expansion here. You'll have a singular part, which is here a polynomial. I mean, it has n terms. So it's a polynomial in 1 over z minus a in this case. Okay, so this will lead towards the power series expansion, the Laurent series expansion of Neuromorphic functions. But before I can tell you, I have to just pause this this example just a little bit. Okay, this is to be continued, and the reason I have to pause it is just because I have to give you the definition of a Neuromorphic function. So a function is said to be Neuromorphic. So yeah, a function, I should write what the domain and the codomain are. So function f from u to c. It's said to be Neuromorphic if it is holomorphic on u, except for an isolated, this is very important, so except for an isolated set of poles. Okay. So here there are several things that are important. Okay. So the Neuromorphic function. So it's an extension of the notion of holomorphic. So it should be holomorphic almost everywhere, except on an isolated set of points, which could be infinite, okay? But it has to be isolated. And more importantly, these isolated singularities have to be poles in this definition of meromorphic. So no essential singularities. If we have essential singularities, we are not called meromorphic, okay? So again, the typical example would be rational functions. Okay, F over G, where F and G are holomorphic. So then you have, so there's an isolated set of zeros for G, which correspond then to the isolated set of zeros, isolated set of poles, sorry, for the rational function. And then these ones will be meromorphic. So the point here now is that they can be understood. So it's an extension of the notion of holomorphic function. And holomorphic functions can be very well understood, as we have seen, through their power series expansion. So analogously, you could wonder, okay, what do we have for meromorphic functions? And we have something called the Laurent series. So a series expansion called Laurent series. Okay. So this is a key notion. And now to introduce them, we go back to our example. Okay, so going back to the example. So you remember, I'm talking about this example here, where we landed in saying that f of z was equal to this thing in the corner here. So going back to this, so let's recap. So we had n, which was this supremum. This had a removable singularity at A. And then we said that, okay, f of z it's equal to, sorry, actually, okay, so actually I didn't have so much more to say. I already said it earlier. Okay, so then we had that this, yeah, we had this power series expansion. Okay. So this was equal to this. Okay, nothing more to say. What I wanted to say was the formal statement. So we have a formal statement. So this example was sort of to understand how you get these, how you can get such an example, right? So along these lines, yeah. So the point is that along these lines you can get the Laurent expansion, this theorem. Okay, so this is a little bit long to write. So let me give the following. So suppose that f is analytic on an open annulus. Okay, so this is the first point where it differs. Okay, so you have such an annulus. So let's do a picture here. Okay, maybe I make the interior circle smaller. Okay, and inside here you have A. So you're looking at this kind of set. So it's analytic on this set. and here you have the R0, and here you have the R1 radius. So first of all, why am I looking at an annulus, right? Well, the point is that when I have this expansion up here, then it's equal to so I divide it into the two parts, okay? And this thing here is called the singular part. Okay, and this one will actually be, so where does this converge? Because here we have, you know, all the powers here, they are to the negative powers. So we have 1 over z minus a and so on. So what would you be able to say about convergence of this series with respect to the point A? So of course, you know, the usual part here, it's convergent on some disk, on some neighborhood of A, right? And we're determined by the radius of convergence. So if we start by that, you know, as a warm-up, so okay, so this one convergent on disk centered at A and with radius R1, okay? And what about the singular part? So the thing is that this one is actually convergent. So it has the least chances of being convergent when Z and A are very close together, right? As you can see, because then we are looking at 1 over Z minus A, which is blowing up to infinity, and you will get to singularity. So this one is convergent when absolute value of Z minus A is larger than some R0. Okay? So it means that you have these two parts, and we say that the whole Laurent series is convergent if and only if both of the parts, both the singular part and the so-called regular part, which is the other part, if both of them converge at the same time. Okay, so it means that you have to be, because of this, you have to be inside the disk of radius R1, so you have to be inside of this. And then because of this, you have to also be outside of the smaller circle. And this means that you are precisely, of course, in this annulus. Okay.
But isn't the singular part finite sum?
So yeah, so in this case, so in this example that I put, it's a finite sum. So now it's fine, yeah. Okay, so could be. So what I mean is that this could be infinite, could be an infinite sum.
Okay.
Yeah, so I gave a remark a bit too fast before I finished the statement of the theorem, but it could be an infinite sum, and when it's infinite, it converges on it. Of course, yes, if it's a finite thing, you have a slightly simpler situation. And the way that you will see this, by the way, is that the complement of this disk, so being outside of this disk here, being outside of this, so being far away, it will actually be seen as a neighborhood of infinity on the Riemann sphere. Okay, so a disk around infinity on C hat on the Riemann sphere. But let me first finish the statement. So the statement is that when F has a Laurent series expansion, around A of the form f of z, which is sum from n equal minus infinity to plus infinity, okay, like this. So this relates again to your question then, that you know it could be an infinite sum. So it has this, and this converges for R0, so for the, yeah, converges on this annulus, basically. And we also have, similarly to earlier, then we have a formula for the coefficient, which is given by the following. Yes. Okay, so this is very familiar formula, right? For you, but note that this is true also for n less than 0. So also for the negative values, this is true. So this just, you know, recall the Cauchy's integral formula and its consequences. You got formulas that looked a bit like this, but now I'm saying that this is true also for negative n. Okay. And then the statement continues with the following remark on the singular part. So I hope it's clear to everybody what the singular part is now. So the singular part, I mean, I never wrote it down formally, but it's the part of the power series expansion where, which has negative indices. So the singular part, so yeah, let me write it, why not? It's this. So this one is analytic. So this is what I said earlier then in the remark. So when you are far away from A, and this actually includes, so I will make this remark here, so including at infinity. Okay, so I will explain what this means. And so you have a singular part and you have a holomorphic part or the irregular part. Okay, so let's call it like that. So this one, so this is just this part. This one converges for absolute value larger than R1. Okay, and the definition is, you know, for the full Laurent series converges means that both the singular and the holomorphic or regular part must converge. This is what we mean by saying that the Laurent series converges. Okay, so then it happens on the intersection of these two sets, which will then be exactly on this annulus. Okay. Sorry.
R1, second.
Yeah.
Please. I think it's less than, no, inequality, sign of inequality.
Hang on. Yeah, there is some, yeah, exactly. Yes, thank you. Absolutely, less than R1. Thank you. Okay, so now I just want to explain what it means this. I'm saying now that it's analytic outside of this disk. So you remember we had this. So we have some disk of radius R0, and I'm saying that it's analytic all the way outside, including at infinity. Okay, so what on earth does it mean to be holomorphic at infinity? So this really merits some explanation. And this is what I will tell you about now, which will give a sort of, I mean, again, it's all about the point of view on these things, right? And again, this will involve then the Riemann sphere, which I think you remember when we were talking about Möbius transforms. how natural they became once we looked at them as functions on the Riemann sphere and the extended complex plane. So it's a bit similar. I mean, meromorphic functions, they are naturally viewed, I think, on the whole complex plane, on the extended complex plane, sorry. So holomorphic and meromorphic functions on this C hat, which, you know, I remind you is C union this point at infinity. It was a one-point compactification. Okay, so this is the Riemann sphere. Just to do a little recap. Okay, so you will remember the Riemann sphere was this thing here. And you had the coordinate axes in this way. And then you had the North Pole. And then let me also put a South Pole. We never used the South Pole last time, but you know, this is the Earth. You have a North Pole, you have a South Pole. So the natural idea here is the following. So now we go and do a little bit of more geometric things, right? So view infinity. So you recall, by the way, that infinity was usually what we call this point n, right? The stereographic projection. But I'll get back to that. So the idea is to view infinity as corresponding to 0 via this mapping z goes to 1 over z. Okay, so how can we view this? So first of all, let's see here. Just check. Let's see here. Yes, I think I want to start by drawing the picture, actually. So the picture would be something like this. Let's see if I do it on the same or if I do it on the next one. Picture would be, no, picture is later. Okay, sorry. So let me start with this. So more precisely. So C hat, you remember it was this unit sphere. N was the 0, 0, 1. S is the South Pole, so it's 0, 0, minus 1. So, okay, so the reason I didn't draw the picture yet was I needed to tell you that we decompose C hat into two pieces. As follows. So we write C hat. Or actually, let me write it on the next page. So we write C hat as S2 minus the North Pole union S2 minus the South Pole. Okay, and now what are these pieces? So S2 minus N, you will remember that this was identified with C via the stereographic projection. You remember that? So you fix the North Pole and then you did something like this until you hit the complex plane. And you identified this point here with this point here. But the North Pole didn't have a natural point in C it corresponded to. It would correspond to infinity. But you had this bijection here, check the biholomorphism, between this first part and C. But then there's nothing that says that I can't define a similar stereographic projection if by removing the South Pole instead, right? So I might as well just start in the South Pole and I might say that, okay, let me take some line here and identify this point with this point. This would be sort of equivalent approach. So actually also this thing here is identified with C. Okay, so I had two overlapping copies of C. So can you all see that this is the case? Okay, and so moreover, these two copies, these copies of C are actually what you call biholomorphic. I will explain to you what that means. It's not hard. So on the overlap, so what is the overlap of these two sets? Well, the overlap is almost everything, just you remove both the north and the south pole. And what is the biholomorphism? Well, the biholomorphism is precisely 1 over Z. It remains for me to explain to you what it means to be biholomorphic. So it means that, so A and B are biholomorphic if there is some map like this, which is holomorphic, with inverse, so with holomorphic inverse from B to A. So it's, you know, it's what you are used to, this kind of thing, this kind of terminology, but you ask that both the function and its inverse are holomorphic instead of continuous or something like that you will have seen in other courses of your life. So this goes towards the idea of a manifold. Actually, what I have said without saying it is exactly that this thing here, this Riemann sphere, is a manifold. And this manifold means that, I mean, being a manifold, for those of you who know, it means that you are locally identified with C. In case of a complex manifold, you're locally identified with a complex plane. And there are this thing called charts. And in this case, there are two charts. And this Z goes to 1 over Z are the transition functions of this chart. Okay, if you don't understand what I just said just there, you will learn about this in the differential geometry course. More about that. But I thought I would say this much. Okay, and then you really identify do this thing that you identify 0 with infinity. I mean, you can map one to the other using this this map. So let me draw the picture, for example. So if I here draw the unit circle, then if I look at what this corresponds, what does it correspond to on the Riemann sphere? So this is the interior of the unit circle, right? So I had this thing. So then does it correspond to, so what is the corresponding set under the stereographic projection, if you remember how this worked? Anyone?
The south half.
Yes, very good. So it corresponds to the south half, like this. Okay. So this is the corresponding set. And then this Z goes to 1 over Z, which is a Möbius transform, right? So actually, so I went to look at this on the Riemann sphere because Möbius transforms are so nice on the Riemann sphere. So then what happens to this set?
It's gonna be the upper half.
Exactly, so it's going to map the southern hemisphere to the northern hemisphere now. Okay, like this. And then if I go back, so with the inverse of stereographic projection, then it means that the image, So the circle is mapped to the circle. Under this map, z goes to 1 over z. But then the interior is mapped to the exterior. Okay, going out to infinity. And this point here, this would be f of infinity, which is the so-called new zero in this picture. Okay, so I can use this map z goes to 1 over z to sort of switch the role of 0 and infinity, is what I'm trying to say with this picture. And then the definition is the following of what it means now to be holomorphic at infinity or mirrormorphic at infinity or something like that. If you can guess, maybe from this picture.
F is gonna be holomorphic or mirrormorphic at infinity if if f of 1 over z is holomorphic at 0.
Exactly, exactly. Very good. So the point is that through this identification, infinity really is a point like any other point, right? And we just have to keep track of the identification. So to write this formally, so we say that f has a pole or a 0 or is holomorphic or is mirrormorphic and so on. So the philosophy is always the same. So I need to get some more space. So pole 0 at infinity, precisely if z goes to, so if f of 1 over z, so if this function has a pole or a 0 at 0. Okay? So this is what it means, and so really the slogan is that infinity is a point like any other, but need to keep track of the identification z goes to 1 over z. So you remember when we said that Laurent series expansion was converging outside of this disk, then it just meant that it was converging on something like in this picture here. And this is then just a neighborhood of the North Pole, which is infinity. So a neighborhood of 0 would look like this, the southern hemisphere, and the neighborhood of infinity would look like this. And really you can see there is no difference. There is nothing special about infinity. The only thing is that in order for there to be nothing special, you have to translate with this dictionary, which is that you have to change a variable from z to 1 over z. In the language of manifolds, you're changing the chart. Okay, so time is up, and I know I always go over time. Let's try to not do that so much this time. Let's just finish by some very simple example, just to, let us write down that. F of z is 3 over z, or something like that. So this function is mirrormorphic on C hat. So being mirrormorphic on C hat, it means that you're mirrormorphic at every point, including at infinity, right? Now, what about the zeros and poles of this thing? So it has a pole of order 1 at z equals 0, because when z is 0, it blows up, okay? But then it also has another singularity, or another singularity, another 0, rather. So it has a 0 of order 1 at z equals infinity, okay, or at infinity, just not to confuse. So why does it have a 0 of order 1 at infinity? Well, it's because f of 1 over z it's equal to 3z, which has a 0 of order 1 at 0. Is that clear how this works? This kind of thing? Should I take that as a yes?
Yeah, it's okay.
Okay, so let's just try one more before we leave. If I write down this. So is this one meromorphic on the complex plane? And what are the zeros and poles and everything? In what points? So it's z minus 5 squared times z plus 7 cubed.
It's meromorphic on C hat, and it has a 0 at z equal minus 2.
Yes.
And it has poles at 5 and pole of order 2 at 5, and pole of order 3 at -7.
Okay, so pole of order 2 at 5, that equals 5. You said pole of order 3 at -7. And is that it?
No, 1 second.
So let me put it, so I will give you as an exercise to check. I mean, obviously you don't have to hand it in, so you can be as sloppy as you want, but check that, so convince yourselves rather that it has a 0 of order. So what would be the 0? I will put this blank. At infinity. What would be the order?
4, I guess.
4, yeah, exactly. It would be 4. It will be 4. And remark, just the last thing, is that 1 plus 4 is equal to 2 plus 3. Okay. Think about that. Now I will leave you with that mysterious comment. It's related also to an exercise on the homework sheet. The homework number 4, which I will send to you right after this, right after lunch. Okay, so let's stop there. We saw some holomorphic, meromorphic functions on the Riemann sphere. We saw some things about the pole of order n, and so on. And then next time we'll look into essential singularities and the residue theorem. And this concludes the experiment of trying to do this, let's say on a tablet, but without it being a complete surprise like last time. So yeah, now the question is, would you prefer, given that I have a possibility, would you prefer for me to do it on the blackboard, or now that you're all at home, is it easier or better to do it on the iPad?
I think the iPad is better for me.
iPad is better for you?
Yeah,
Okay.
I think the iPad is better too.
Okay. Does everyone agree with this?
Yes, iPad is better. Yes, iPad is better.
Okay, good. Okay, yeah. So the only disadvantage with the icon is that echo here maybe. Yeah. Thanks. So as far as I'm concerned, the only disadvantage with the iPad is that I'm slightly slower than I would have been on the Blackboard. I don't know if this is something you notice or not, but I think I would have covered another 2 pages probably on the Blackboard. Is this noticeable, that it's slower?
Yeah, it's not so, and also like having a lecture on an iPad, it reminds me of the lockdown.
It reminds you of a lockdown, yeah. So you would prefer it to be not on the iPad, maybe? Do I
Yeah.
interpret
I
you
think
correctly?
it's slower because we are asking more questions on the iPad.
You're asking more questions on the iPad, yeah. No, I noticed this, and that's one reason why I thought maybe it was worth to give a shot. Maybe you prefer this. Yeah.
I have a question about the homework. Are we still putting it on your mailbox today?
Yeah, you can put
Because
it
you're
in my
not here.
mailbox, but you can also put it, I mean, you can also send it to Alejandra. I mean, to send it to both of us if you want, because she's the one who's correcting them nowadays. So.
Okay.
But you meant my mailbox, you mean the physical one? Is that what you meant?
Yeah.
Yeah. Yeah, so you can do that if you want, yeah, absolutely. And for those
Okay.
emailing, you can email to either of us. Yeah, so it's good. Okay, but so just to be clear, I mean, how many votes iPad and how many vote Blackboard, or is there not a big difference? I mean,
I think we should type in the chat.
yeah, type in the chat, please. Yeah. Okay. And you can also say if you don't have a strong preference, you can also write that. If it doesn't matter. Okay, any? One, two, three, four, five. So we have 7 votes. Let's see here. And the remaining people? Any vote? Okay, so it seems kind of overwhelming that people prefer the iPad, I would say. So in that case, yeah, I will try to do it on the iPad from now on. I mean, I cannot promise I will always do it on the iPad because you know, maybe for some reason. Well, so my fiance is also teaching at the same time, and sometimes we bother each other if I have to be at home. So if I have to be at home, you know, I'm not sure, but I'll try to do it on the iPad to use it whenever I can. I'll think about this. So, any other questions before we hang up? Before we leave? Okay, so if not, then thanks for this different lecturing experience on the iPad.
Excuse me?
Yeah, sure.
Yeah, actually I want to ask, after the residues theorem and essential singularity, what are we gonna discuss after that?
Yeah, so it depends on the time, but the plan after that would be the argument, I mean, something that's closely related to residue theorem is the argument principle, Rouché's theorem, this kind of stuff, and then automorphisms on the unit disk is a very nice topic that I would like to cover. So the way the course is going, so we just finished lecture 10, and I would say that mainly, so up to lecture 8, we were more or less on track. Now I would say we are between a half lecture and a full lecture, maybe behind last year, mainly due to this iPad business, and the last time was kind of a disaster, right, with technology. So we are slightly behind. So, you know, the bonus topics at the end are in slight danger, I would say, especially if I am to continue on the iPad, but since it's a bit slower. But we'll see. I'll try to do as much as possible. But for sure, I will do also the automorphisms on the unit. This is a very nice.
Okay,
nice
thank you.
Yeah. Okay, and yeah, some of you already handed in the homework via email, I saw, and you can also hand it in in the mailbox if you want, and I'll find them on Friday, I guess, which is the next time I'll be there. Okay, so see you all on Friday then. See you all on Friday then.
Okay, I hope you feel better soon.
No, actually, so I woke up with coughing a little, and I just didn't want to go out, you know, because nowadays, if you walk around ICTP coughing, people will be unhappy at you, right? So, that's it, but I'm fine.
Yeah, I noticed this even in the town.
Sorry?
I noticed this even in the town when you like cough, that people scared at you.
Yeah, no, you don't want to do that. So it's just, you know, whenever you have a sniffle or something, okay, I stay at home, I lecture with the iPad, I thought, you know, why not? So, but also I wanted to anyway try this to see if you preferred it, which you did. So, okay, so see you on Friday. Thanks, bye.
Thank you.
Thank you.